Hello, everyone. My name is Amir-massoud Farahmand, and welcome to this course on machine learning. Maybe I can give you a little bit of introduction to you about myself, and then we can start the course. So my name is, well, I said Amir-massoud Farahmand. I'm an assistant professor at the Department of Computer Science and a research scientist and faculty member at the Vector Institute. So my work is mostly on reinforcement learning, especially from theoretical perspective, but also I worked on other areas of machine learning, like say regression and data deep time series and things like that. Let's maybe start with, so what I'm going to do today is start talking about like what machine learning is and why we need machine learning. And then we talk about some specific method, especially K-nearest neighborhood, and we go from there. But maybe before I continue, is there any question that you want to ask? Also, maybe I check that if it's actually being recorded. It is recorded. Yeah, it's a bit annoying because I don't see all of the screen in two different. Okay, seems to be recording. Okay, any question? Just, I guess it might be too early to have many questions. Okay, so this course is supposed to be very interactive. I want your participation in the course. So in many points, we stop and talk about some concept. And actually, I want you to think about these concepts and try to kind of develop algorithms yourself. And then I may help you in doing so. So I think one of the important things is that when we talk about machine learning, we usually think about machine learning in the context of AI. Like we use machine learning to develop intelligent systems, AI systems. So, but now the question is that what does it mean to have an intelligent system or intelligent agent, the terminology that they use. So any ideas? Yes. Okay. Okay, so that's one good idea. Yes.
Maybe something you give it one input, and then if you ask her to do the same thing again in the future, it's potentially better than the first time.
Okay, so it's like you get, if you ask a system, you give some input to a system, and then if you ask it again, it will give you the same answer?
Well, I guess.
Okay. Yes?
System will be able to learn from previous information, and if you work with another information that you can put some rules and algorithms, or from learning from interaction.
Okay, that's good. So there was another. Yes.
I think it's a system that is giving tasks and way to it's how good or how bad this task is being performed.
Okay. Okay, these are all good ideas. Oh, yes, so there is another.
A system that can imitate human cognition, like in other words,
Okay, so that's good, but then I guess you need to define what thinking means. So I think basically you refer to intelligence of an agent or artificial agent to doing what humans do, essentially. Okay, so these are all good. So I mean, I'm not going to give you any answer because probably there's no single answer for different perspectives. Also, there is some answers on chat. Let me try to see. So, okay, so I guess some of these things is that, yeah, I think that there's a problem that they can't probably hear you very well. I try to repeat some of your questions. So, but some of the questions here or answers is that an agent which can understand new scenarios based on past experiences. The other is that it can learn from user responses. Okay, the other one is that if we define intelligence as the ability to predict outcome of a process or action based on its initial state, then we can define an intelligent agent as a system that has the same ability. An agent which can predict new scenarios based on past data, and intelligent agents capable of making decisions. Okay, so I think these are all good. I don't know how much we can do about not hearing the questions here. I try to repeat some of them, but well, given that I couldn't connect my iPad, so probably I can't do much about the audio of quality here. So these are all good. Maybe I give you one perspective and then try to put this course in that context. This perspective is a bit non-traditional, but you will see what it is. Okay. Okay, suppose we have an agent, we have an AI agent. It might be a robot, it might be a car, it might be a computer software agent on the web or anything. So this system, this agent, receives information about the world. So for example, if it has cameras, it kind of gets information about the world through its cameras. Or for example, if it's a car, autonomous car, it receives information through cameras and LiDAR and other sensors that it has. And then what happens? Then it takes an action. And as a result of taking an action, its state in the world changes. So it decides, for example, to move forward. And then the result would be that it moves forward. What's the goal of this agent? The goal of this agent is to achieve some kind of long-term performance or long-term reward. So this agent is in its environment, observing it, taking actions, and making a sequence of actions until it gets to a lot of reward. So this is what basically, this system that I described is what basically I usually use if I want to talk about reinforcement learning and what reinforcement learning agent is doing. And this is the kind of a little bit unorthodox part that I would claim that the problem of artificial intelligence and the problem of having reinforcement learning agent, in the sense that I defined here, it's very broad, they're almost the same. So what you have is that what you need is to have an agent that is going in environment, observing it, taking actions, and wants to achieve some goal at the end of the day. And but to do so, it may need to solve some problems, some decisions that are kind of tough. It is not clear what the outcome of it would be, but the goal is to, at the end of the day, get to that goal. So if we want to make such an agent, this agent needs to have some capabilities. What are the capabilities? Okay, so one of them is the capabilities that it needs to be able to predict how the world works. For example, if it sees an object, it should be able to say whether that object is, say, if it's a car, it's a human, another car, or it is just something irrelevant. Or, for example, it needs to predict events, the probability of events happening in the future. For example, if it's a robot, the robot is moving in this direction, it should be able to predict if I move for 5 more seconds, I will hit that wall or not with the current speed. So basically this agent should be able to say something about the board and try to be able to, in most situations that it might be in, it should be able to say something meaningful about the state of the board. Okay, so this is one part of this agent. The other part is the planning. So it should plan its action in order to achieve its long-term goals. So it knows what happened in the board because it can predict what happened in different situations, but also it should be able to plan based on, in order to achieve its goal. So this agent, this prediction and planning are two parts of, two important capabilities of this agent. And what we do in this course is mostly focusing on this first part of it, which is predicting how the board works. And doing it, we will see, by learning how the board works. So prediction, not in a way that we write a program that says that if the robot moves say for 5 seconds, it will hit a wall, but learning that it happens based on the data. So this is a bit, I don't want to say controversial, but not a usual way to introduce a course in machine learning, because I started basically from my usual introduction to a course on reinforcement learning, and then divided 2 parts. This part is the one part of it, the prediction part is the course on machine learning. But also you can say that machine learning is more general, so reinforcement learning is a subset of machine learning, but the content of this course is mostly focused on prediction, though I will talk about reinforcement learning at the end. So any questions? Okay, so okay, so one question. Oh yeah, so I guess, so what are the questions? Do we turn on your microphone to ask questions if there's any? Yeah, let's try that. I increase the volume so maybe others can hear. Yeah, try that to see how it works. The other is that other question is that do intelligent agents also need to be able to take actions? Yes, so I guess that one part of it was taking. So this take action and its state changes. So otherwise it would be somehow like a passive agent. So it would observe things, but cannot do anything. Though, so yeah. Okay. Is classifying an object really a type of prediction? You can say that, yes, because you predict, you can see it as a type of prediction problem. Because you're saying that one input, you predict what label it is or what type of object it is. And especially this is kind of interesting or important because you probably haven't seen that exact object previously. So it is not, you can't be very certain about it. Okay, so any questions here? Sorry, what's the reward of the agent?
What's the bond? Like what part is the reward? It's what part belongs to the reward, what part belongs to it's critical or something else.
Right. Okay. So the divide between environments. Okay. So I guess the question is that what is the boundary between agent? Where agent ends and where the environment starts? So this is actually a very good question. I don't want to get into it, but there are different ways to define it. So there's no So that boundary is essentially somehow abstract concept. It is not necessary that the robot is the agent and the physical world is the environment. You can actually think about a subset of the robot is the agent, and even the rest parts of the physical robot is the environment. But depending on the task, you can define that boundary different ways. But I don't want to get into that very much, how we can define it, but it's more like an abstraction, not necessarily corresponding to some physical demarcation. Okay, so what is learning? So this is not necessarily, so there are many different definitions of what is learning. So a dictionary definition would be something like that: the activity or process of gaining knowledge or skill by studying, practicing, being taught, or experiencing something. So this is not a bad definition. I guess it incorporates many things that we talk about usually, machine learning, but not in a technical terms. Maybe a bit more technical terms, but maybe somewhat too abstract, at least at this stage, is this other definition by Tom Mitchell, which says that a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P. So we have experience, task, and performance measure. If its performance at task T, as measured by P, the performance improves with experience. So we say this is the task, this is how we measure you, and this is the data. If we give you more data, to solving this task, according to this performance, your performance should increase if you get more data. So this is kind of another way to think about learning. Okay, so again, what is machine learning? So I think in that division that I had, or what an intelligent agent should do, in the task of prediction, we can always write a code to say that in these situations, this should happen. For example, if you have an object of apple and orange, you can write a code that takes the input and classifies it as an apple or orange. Okay, so how do you do it if you want to write a code? Not a machine learning solution, but a simple solution. How do you classify between apples and oranges? Yes. Yeah. So not necessarily.
Red apple.
Yeah. So I guess that's a good one. And if it's orange, then it's orange. But then, depending on the lighting, or not all apples are red to start with. But that's a good kind of features to think about it. So that's one solution. But now think about more complex problems. So for example, if you have, I don't know, if you want to recognize desks or tables, how do you recognize it? I mean, there are many different types of tables. Not all of them have the same number of legs. So you can still try to write a code to recognize tables. But then, as you see, it becomes a bit more complicated. Or many other things. I mean, if you want to say, for example, the person is happy or angry by just looking at his or her face, like an image of it, you can try to write your codes somehow to figure out that maybe look at the eyes or look at the mouth and the shape of it. I mean, these are, even taking the shape of it is not a trivial task. But even if you can't do it, it is not easy to say whether a person is happy or sad or angry by just writing a few bunch of if and thens. So the idea of machine learning is that, okay, so this machine learning approach would be to program an algorithm to automatically learn from data or from experience. So instead of writing that code, we write an algorithm that finds the relation between input and output and be able to predict essentially if you get this type of inputs, that you haven't seen before, the output should be like this. Okay, so why we might use machine learning? For example, I guess if the code is hard, it's hard to code the solution by hand. So I guess I mentioned some of them. The other is the system needs to adapt to a changing environment. So which means that environment is changing. So your new types of desks or in this environment or table environment is different from what you had seen before. But you still need to learn fast that these are tables. Or for example, we go to a new region and the way people talk, they have different accents. And then you want to kind of learn fast what they are saying. Okay, so also maybe you want to actually perform better than what human can perform, or maybe a human can write that code to perform that thing. And there are issues related to privacy or fairness. So, for example, when you write a code solution yourself, you probably induce the biases that you have into your how to solve this specific task. Like whether a person is happy or angry, you may have the bias that focus on, say, eyes, but maybe not all people have. Eyes is the most important factor for deciding whether they're happy or not. I don't know. But so these are these issues too. Okay, so there are some questions. Okay, so I guess that was the answer. Look at the color that has a majority of pixels, maybe for Apple and Orange. Using image features of Apple and Orange, yes, that's good. Okay, so I guess these are a few of them. We can abstract common features of that object that leads human to decide what that object is. So that's, I'm not sure if it was Orange or Apple and Orange task or not, but yes, so I guess we can do that, except that we have to find that abstraction. Okay, can you give some examples of what are not achievable in machine learning at present compared to human programmers? Compared to human programmers or compared to humans? I mean, compared to humans, many things, like basically humans are much more intelligent systems than computers right now in most tasks. But for computer programmers, I guess, I think many things actually. So if, for example, if I ask you to write that face recognition thing task, happy or sad, it's very likely that humans cannot actually write a good system, or even recognizing some object or digit recognition, like whether it's 1 or 2 or 3, by looking at the image. I think it would be very difficult to actually write that code. Is experience different from data? So that's another question. Maybe to some extent, or maybe the emphasis would be a bit different. So experience might be, they're almost the same, but not all data is in the form of experience. So when I use experience, but this is not a kind of common terminology, this basically means that so there is an agent interacting with the environment, observing, taking actions. So that sequence of observations and actions, that's more like an experience. Okay. I think making 100% accuracy in machine learning would be challenging, that's true. But that's the same for humans. Like most humans cannot also make 100% predictions. Yes.
Can you give an example of what could be some data that the agent consumes that is not part of the experience?
So some data that the agent can assume that is not a part of experience. Yes, I guess that's actually relatively, well, it is common in some way. Basically, we put our prior beliefs about how the problem should be solved into say, our algorithms or into our machine learning models. So we will see some form of it that, for example, we say that essentially we see that the solution would be in the form of, I mean, there are many different contexts, so I can't summarize all of them, but essentially saying that there are simpler solutions are preferred. So we impose that type of prior in many machine learning. But then what simpler means in different contexts would be different. Okay, so let's. Okay, so also machine learning, let's have a kind of comparison with statistics. There's a lot of similarity between machine learning and statistics, like traditional statistics. And actually the boundaries between these two fields are not very strict. But so both fields are trying to uncover patterns in data, more or less. Both of them use very similar tools in the math, like calculus, probability, linear algebra. And many of the algorithms are the same. So many of the algorithms I'm going to talk about have been developed by people who are traditionally known as statisticians and not necessarily, and don't necessarily identify them as machine learning researchers. But it is not statistics. So there are some ways that we can say what are the differences. And this is kind of like high level. So it's not always true that, for example, I'm saying that statistics is mostly concerned with helping scientists and policymakers making sense of data, making good conclusions. But machine learning is more about, concerned about making agents, autonomous agents that can do things or make decisions and be accurate predictors or things like that. So you can think of statistics traditionally has been there to help scientists, but machine learning is to make things more like AI systems. There is more emphasis on interpretability and on statistics, but machine learning with more emphasis on predictive performance. So, because for scientists, it is important to say, you see a data, you want to find why you observe certain things. So, for example, you want to figure out the relation between genes and certain disease. So you want to know what genes are important in being good predictor of that disease. So getting to 2-3 genes is very important for them. But from machine learning perspective, that may not be the most important thing, but would be having a, say, computer system. Then you give your gene data to it, and it will tell you what's the chance of having this disease in the future, even though it might be a very complex relation of maybe hundreds of genes, not necessarily 2, 3, 4 that are the most relevant. But I want to say that the difference is kind of blurry. So it is not exactly like people in machine learning work on making interpretable machine learning systems, and also people in statistics care about having a good predictive performance. Okay, any questions so far? So there is a question here. Okay, so I guess it was. Okay, so another thing that I want to talk about is the relation to AI. I somehow started from relation to AI to some extent, mostly from perspective of AI is almost equal to reinforcement learning. So what's the relation of reinforcement learning to AI? But now what I want to say here is that machine learning people kind of say machine learning and AI are the same, more or less, at least in media, but they are not exactly the same. Like machine learning can be seen as a part of having an intelligent system. but there are aspects of AI that do not use anything learning-based. For example, we have symbolic reasoning, rule-based systems, tree search, which do not have any learning components. Okay, so what's the relation to human learning? So the relation to human learning is that, well, humans are very good learners. So we are very data efficient. We can solve some problems by just doing things a few times, which basically you can think of it having a few data points. We can learn the relationship. For machine learning systems, you need hundreds, thousands, or sometimes millions of data points to get to similar performance. Also, humans are very good in solving a wide range of tasks. So, for example, we have good vision, we have good language understanding, we have a good motor control relative to some animals. We are not as good as monkeys, probably, or motor control. But then also this process is taking a long time for humans to basically fine-tune all their learning systems to be able to function. So that's a process of development, takes many years, 10, 20 years to get to kind of the peak of our performance, maybe. So one other thing that I want to mention here is that many machine learning methods, or some machine learning methods, try to borrow ideas from how humans learn. But as you will see in this course, not all of machine learning methods look like anything that humans might do. So the one that might be closer to how humans learn is the neural networks and deep neural networks and deep learning. But then even if you compare them, you see that this is not necessarily how a neuron in an animal works is similar to a neuron in kind of artificial neural network. Conceptually, they behave the same, but they are not the same. And it may perform, a machine learning system may perform better or worse than humans. So 10 years ago, I would say that most of machine learning systems would perform worse than humans, but there are certain things that I think they can do better than humans, some specific tasks. Okay, so is there anything that you want to discuss? Okay, so there is one common way of classifying or categorizing different machine learning methods, depending on what type of problem they want to solve. So one is called supervised learning, which we have access to labeled examples of the correct behavior. So for example, we have a bunch of images of apples and a bunch of images of oranges, and we know that these images correspond to apples, these images correspond to oranges. So that's one thing, that's supervised learning. And most of this course, or a good fraction of it, probably 70% of it, would talk about supervised learning. So the other one is that reinforcement learning. So learning system, which we usually call agent, interacts with the world and learn to maximize a reward signal. So in reinforcement learning, we don't usually say, oh, you should do this action to achieve your rewards. But we only at the end of, we say that it does set of actions, and at the end it receives whether that was a good set of actions or not. So essentially we give feedback in the form of good or bad. And then there is this unsupervised learning, which we don't have any labeled example, but we just try to find interesting patterns in data. So an interesting in different contexts mean different things. But just to give you an intuition, for example, we give a bunch of images of apples and oranges, and maybe some other images of, say, tables and cars. But we don't tell the system, the computer, what each of them are. So then what happens is that the machine learning system or unsupervised learning algorithm should somehow cluster each of them based on some similar shapes. So maybe it puts apples and oranges in one category or cluster because they look like similar to each other. So that would be the cluster of maybe fruits, even though it doesn't know that's fruits, but these look the same. And then the cars would be another cluster, and tables and desks and chairs might be another cluster, without being told what are the right labels for each of them. So unsupervised learning is a bit more vague because there are different ways that we can define what interesting is. Any question? Okay, so I like you to be more active. Up to 10 minutes ago, you were so active. I don't know what happened. Yes.
Example of reinforcement learning in like actual application.
Practical application like that actually people use.
Yeah.
So there can be many. So there are robotics example, like learning how to grasp an object by trial and error. Like if the robots try to grasp it, fails and up. It's like not completely until it can pick it up. So these are the things that people have done it in their research labs. I'm not sure if they do it in factories or not. The other thing that is more, maybe people done it in limited kind of deployment is for data centers. Like you want to maximize or minimize the energy consumption of a data center by deciding when to cool down the room and things like that. So some people have worked on that and they deployed in unlimited cases, like certain data centers. But yeah, I would say many of them, and some form of reinforcement learning, especially you can think of a special case of reinforcement learning has been used in showing you advertisement on the web. So essentially, the system learn how to maximize your chance of clicking on an ad by deciding what ad to show you. So this is like reinforcement learning. You can formulate reinforcement learning because the reward from that agent is you're clicking. Its action is that what set of ads it should show you. But just showing that it learns to maximize. But there are some differences that you can consider as not a full reinforcement learning problem, but they call bandit problems, or multi-arm bandit. Yes. Sorry, the labeling. Right. Yes. So by labeled example, I mean we have this input like apple, and label that this is called apple, and orange, this image of orange, and this is called orange. So this the name of apple or orange, that's a label. But we actually see it a bit more in a more formal sense. Okay.
I have a question.
Sure. Yes.
What is the difference between deep reinforcement learning and reinforcement?
So what's the difference between deep reinforcement learning and just basic reinforcement learning? So that's the difference is basically whether we use deep learning methods or deep neural network as a part of a reinforcement learning system or not. I think it might be a bit too early to describe what deep learning is unless you had seen it before. But it's essentially, we can think of it, if you use a neural network, so this one, it may borrow ideas from biological systems, so neural network. If you use neural network, those systems are called, in part of the learning, those systems are called deep learning systems nowadays. And the deep comes from having many layers of these neural networks. I will explain what they are in, I guess, 5 or 6 lectures. But then if you solve a reinforcement learning problem and you use this neural network as a part of it, that is called deep reinforcement learning. But that's the kind of difference. So you can think of it as a subset or special case of reinforcement learning. Okay. So there are a lot of questions. Okay, so self-supervised learning, let me skip that. I mean, a semi-supervised learning to, yeah, I guess it might be a bit too complicated here. So for example, semi-supervised learning would be something between supervised learning and unsupervised learning. You have some labels, you don't know, but not for all your inputs. For some of your inputs, you don't have any label. So that would be more like semi-supervised. Self-supervised is, yeah, let's skip that. Is reinforcement learning where the agent is provided a goal but not told how it should do it? Yes, that would be reinforcement learning. So we basically say, if it achieves its goal, we say that's a good job, or bad job, it cannot achieve it. It's essentially the same way that many humans or many animals, I guess, learn how to learn skills like dogs, or if your dog can't do a trick, that's an example of reinforcement. Or learn how to do it, that's an example of reinforcement learning. Or if you're, for example, learning a new skill in soccer and trying to shoot the ball until you can pass it to a person 30 meters away successfully. You do it many times until your brain learns how to do it. Your reward signal would be whether you achieve that successfully or not, and kind of try to adjust it. So for reinforcement learning, is this reward signal predefined? Yes, at least my kind of a simple answer is yes. So the environment gives the reward signal, or if we design a system, we define a reward signal and we give it to the agents. Okay, yes, so there's an answer to that. How does the agent understand a reward signal? What does that look like practically? So let me get back to this closer to the end of the course when I actually formalize it mathematically. Yeah, so but the answers are good. Sorry, I have to. Do we put the regression problem in the supervised learning category? Then what's the interpretation of data labels? Yes, regression problem would be an example of supervised. The label, it would not be labeled like an apple or orange. It would be a, say, real valued number, like 5.33. So that would be the label or the target here. Okay, good. So let's move on. So there's a history of machine learning. Started from 50s perceptron algorithm, and then Arthur Samuel wrote a program to learn how to play checkers. The checker play wasn't so good, but good enough to defeat him. And then there is this book called Perceptrons by Minsky and Papert in '69 that basically criticizes the neural network at that time. So neural network is very old. Like we had in 50s, we had neural networks. But then like the perceptron algorithm can be seen as one form of neural network. Minsky and Papert, so this is interesting because they criticize neural networks and they say that they cannot achieve something. And they effectively killed the field for a while, for a decade or more. Because people said that, well, that Minsky is very, I mean, both of them, but Minsky is a very important person in artificial intelligence, one of the founders of AI. And he said that this is not going to be useful. People listen to him, and then the progress stopped for more than a decade. But in the 80s, many other things happened. So for example, the backpropagation algorithm, which is rediscovered, we can say, by Jeffrey Hinton at U of T and some other colleagues, that showed that the limitations that Minsky mentioned can be resolved. So that was a rebirth of neural networks. And a few other ones, like the Pearl Bayesian network, that's another important thing. Or there is a concept of PAG or PAG learning, probably approximately correct learning. So that concept was introduced also in the 80s. So many of the foundational things happened there. So then again, 90s, people became less interested in AI. So we may call it AI winter, but it wasn't a complete winter because many of the kind of modern algorithms were developed at that time. For example, Markov chain Monte Carlo, variational inference, kernel methods and support vector machines, boosting and convolutional networks, they were developed there at that time. So we talk about some of them, like we talk about support vector machines and boost and kernels, probably boosting for sure. We talk about it, and maybe we talk about convolutional networks. So in 2000s, people in applied areas of AI, like computer vision, natural language processing, speech, they started using machine learning-based techniques in order to solve their problems instead of writing the rules themselves. And then in 2010s, it can be considered as a deep learning revolution. So deep learning is essentially neural networks with large depth. And you will see what depth means here. So so the technology or the ideas were there from many decades ago. So like in 50s, we had neural networks. In 80s, we had the basic concept like backpropagation that is required in making deep learning systems work. But the name was so this is interesting. I guess the name was introduced, if I'm correct, like middle of 2000, like 2005 or 6. Hinton, I believe Hinton published some papers with that name in it, but that they were essentially deep learning, neural networks. But in all intents, they become very successful, so that essentially they started to dominate the whole field of machine learning, and many of the methods that we use in machine learning are modern methods that we use, or maybe better way to say. Many times when we want to use machine learning to solve a problem, we use a deep learning method and not something more classical ones. Okay, so I try to go a bit faster. So machine learning is very popular, become popular. The conferences like machine learning conferences, the number of people register for it kind of grows almost exponentially fast. So there is this conference called NeurIPS. The conference was sold out in 11 minutes. So this is kind of 2018. And there are many applications in computer vision. Many areas of AI, computer visions, for example, how to detect objects, how to estimate the pose, or many things that you can think about regarding images. People do it using machine learning. In speech recognition, for example, if we want to convert speech to text or identify the speaker, machine learning is used because you can't practically write a code how to do this. In natural language processing, machine translation, or sentiment analysis, like deciding whether this text is happy or not. For example, a review posted on Amazon, whether it's a positive review or negative review, not looking at the score, but just the text. That's called sentiment analysis, or detecting spams. Many of these use machine learning, and also in playing computer games. So AlphaGo is an example of using reinforcement learning system to learn how to play the game of Go, which was considered to be a very complex problem for any AI system. And application recommender systems, like when based on your previous selections, Amazon, Netflix, and many other companies suggest you some new products to buy, and it's in their interest to suggest you good products. They use machine learning for doing so. Okay, so any questions so far? Maybe we can have actually a break for a few minutes, and then we start maybe in 5 minutes. Now it's 12, but 2 past 12, so maybe we start 7 past 12. Okay, so let's move on. So why this class? So there are other courses at U of T for machine learning. Some of them are more advanced, like for example, we have a neural network course. So maybe you say that why not start from neural network? The thing is that this course provides a foundation of machine learning. And the principles that you learn in this course will be essential in learning any other courses in machine learning. So the other thing is that even though many people these days use machine learning, neural networks to solve their learning problems, but then in practice, you actually probably need to start using simplest methods to see if it works or not, and then after that, you start using machine learning. And so yeah, okay, so there are a lot of things that we don't discuss here, but many of the foundations are built here. And so this is another example that, so Kaggle survey a few years ago that seeing what methods people use in order to win Kaggle competitions. So Kaggle is like, there's these competitions that you need to use machine learning method to solve some problems. And the practitioners use methods like logistic regression. So this is a percentage that they use. So logistic regression, decision trees, random forest, and then just neural network and other techniques. So these, like the first 3 ones we are going to talk, we are going to also talk about neural networks, but just one lecture. And many other methods like Bayesian techniques we talk a little bit about. Ensemble methods we talk about, support vector machines. We talk about boosting, but not gradient boosting. Convolutional nets, we talk about recurrent neural nets, we don't talk. If others, I don't know. Evolutionary approaches, we don't talk about. But you see, basically, many methods that people use in practice are discussed here. Okay, so let's talk about a general workflow of machine learning, like if you want to solve a problem from a practical problem, what you have to do. And then we go on talk about one specific machine learning method. So the first question that you have to ask is that whether you should use machine learning for this problem or not. So is there a pattern that should be detected? Or maybe you can find the solution analytically. So for example, if you want to say, predict the trajectory, if you throw a ball, predict the trajectory of it, do you need to use machine learning? Probably not, because we have Newtonian mechanics. You can use Newtonian mechanics to essentially find a very good solution for that. But for maybe some other problems, it becomes more complicated. The relation, you can't find the analytical solution. So for example, I mean, this is a recent trend that for some complex physical systems, like if you have a turbulent flow in kind of aerodynamics, you want to predict how, say, air flows or some other liquid flows around an object. You can't usually find an analytical solution. You can try to write simulators to solve the physical equations and predict what's happening, but that's usually very complicated and computationally intensive, though you can do it, and people have done it for decades. But the more recent trend is that we use machine learning methods to have better predictions and faster predictions. The other question that you have is that whether you have data or not. And if you don't have data, there's no point in using machine learning algorithms. So after you detect that or determine that you need to use machine learning or not, then you need to gather and organize data. So gather your data, frame it, pre-process it, visualize it, look at your data. Visualization is very important because sometimes by just visualizing your data, seeing the relation between different variables of the data, you get a lot of insight about what kind of problem it is, even before applying any machine learning methods. Then you need to establish a baseline. So what level of achievement is considered reasonable or okay. And then after that, you can, if you have an algorithm that performs better than that, that would be a success. Then we need to choose a model, loss function, regularization, all these things, which we don't know what they are, but we are going to talk about it soon, as the main components of your machine learning. So a machine learning algorithm has a model, it has something called loss function, it may have something called regularization, and then after that, you need to usually solve an optimization problem in many cases, but not always. So if you solve an optimization problem, which might be an easy problem or might be a complex, complicated problem, then you get a solution. But your machine learning algorithms usually have something called hyperparameters. So these are parameters that you can tune to change the behavior of your machine learning algorithm. So you need to do a hyperparameter search, tune them in order to make the performance of your machine learning algorithm as high as possible. And then you need to analyze performance, debug it, and then see whether your performance is reasonable or not. And if it is reasonable, then that's great. If it is not, you need to iterate back to step 4 or 2. So maybe you need to change your model. Maybe you need to use a different machine learning algorithm, or maybe the issue is not the method or that you use, but it is the data that you have. So maybe you need to have better data, maybe collect more data or pre-process them, clean them in a better way. So actually, this is very important. Like machine learning without enough data does not work well. In many cases, doesn't really. If you don't have enough data, no method would perform very well. And if you have a lot of data, many methods perform reasonably well. Of course, there would be a difference between them, but important factor is the data that you have. So, any questions so far? Okay, so I'm trying to answer some of the okay. Okay, so I try to skip in person and online should be typed in chat. Okay, so question is that about the course. I think I feel this more programming heavy or math heavy. It has the, maybe I talk about it later. Are we going to study most of these in the course? We talk about many, I'm not sure about these means all these steps of the flow, of the workflow or not. If that's the interpretation, we will be focusing on the methods like the models, loss, and regularization. And we talk less about like how to gather data or visualize. Like basically, we don't do it much, but you will practice it in your homework assignments. And maybe I answered the other questions. Is it programming heavy or math heavy? The lectures will be math heavy, so I don't talk about programming much. It's not very math heavy really, but there's no programming in it. Your homework assignments, I'm going to talk about, it has both derivation part, so math part, and programming part. And I think the time-consuming part will be the programming part for most people. Okay, so, but we talk a lot about different models, different loss function. We talk about optimization. We talk about hyperparameters more. But generally, so the question is that what do you mean by hyperparameters? We will see what I mean. I give an example if I have time today, but basically, this is the parameters of a machine learning algorithm that you tune, you say how this machine learning algorithm should work. But you will see what I mean. Okay. Okay, so let's move on. That's good. These are all good questions. I'm sorry I can't answer all of them because I think some of them will be clear. later. Okay, so another thing is that in this course, you need to we derive many algorithms, and in some of your exercises, you may need to derive some simple algorithms based on what you have already learned. When we want to implement them, we usually try to use like array processing. So we do vectorize the computation and use tools like NumPy in Python in order to benefit from like faster computation that we can do. So for example, I mean, this is the programming details. So I said we don't have much about programming, but there are a few slides here. So that's one of them. So for example, we can write the, say, multiplication of two vectors, a matrix and a vector with some for loops. But we can also write like using NumPy's dot command to do it much nicer and also much faster in Python. If you wanted to write this in C or C++, that wouldn't matter. Like essentially, dot would be translated to for loops in C, C++, or Fortran, or those lower level languages. But in Python, for loops are super slow, and we usually use Python in most of our codes in machine learning because provides a very good high-level programming language to implement our algorithms. Doing it with C or C++ would be very cumbersome, unless we want to, the performance is real bottleneck. Okay, and so when we want to implement machine learning systems, so this is again a bit about software, how we write the programs. There are a lot of frameworks. Many of the algorithms we talk about have already been implemented because many of them have been around for many years, decades, some of them. So one of the tools is called scikit-learn. So this is a Python tool framework, and it implements many of the machine learning algorithms we talk about in this course. So we can use it. So many of the things that we talk about would be only a few lines of code on scikit-learn. For neural networks, we have also frameworks for implementing neural networks like PyTorch, TensorFlow, Theano, JAX, and things like that, that basically do many of the complex computation that we need to do in order to implement a neural network. You will see later that some of the derivations for neural network can be quite cumbersome if you want to do it by pen and paper. So they do these things automatically. But then in this course, essentially, in some of the exercises, I may ask you to not use these frameworks, but implement things yourself so that you get a better sense of how these algorithms work. Okay, any questions so far? I'm going to talk about logistics at the end. So any question about these things? Okay. So I guess the question is that auditing the course. So unfortunately, you can use it Zoom. You can connect through Zoom virtually. But if you haven't been enrolled in the course, I would ask you not to come to the classroom. So to make sure that the room is not very dense. Other courses, they would say no. But here I'm willing to say yes, but only virtual. As a non-computer science major, real assignments cover much knowledge on data structure and algorithms. Well, I guess it depends on the algorithms. If you're comfortable with writing a Python code, that should be okay. You don't need to know, say, algorithms on graph search or complicated data structure, but you need to be comfortable working with matrices, vectors, things like that. I guess you will see. So we will have a homework assignment soon in the next 1 or 2 weeks. And you will see whether it is difficult or not. All right, so let's talk about our first machine learning algorithms. And through it, we introduce the basic concepts in machine learning too. So this method, this class of methods called k-nearest neighbors methods. But let's talk about first how we formalize a machine learning problem. So in this lecture and the next few lectures, I'm going to focus on supervised learning, which means that we are given a training set, which is consistent of inputs and corresponding labels or targets or outputs. So for example, in object recognition tasks, the inputs would be in the form of images, image of apple and orange, and labels would be object category. So this is apple, this is orange. And for example, for document classification, the input would be text, right? You get a text, and the label would be maybe you want to figure out whether this text is political news, sports news, or it's a fiction or something else. So that would be the category of that text that someone has labeled it already. And maybe if you want to have a system, supervised learning system to convert speech to text, the input would be audio waveform. So it's a kind of signal that encodes the amplitude of the audio. And the label would be text that is corresponding text of that audio. So let's maybe think about like how images work or look like to a computer. Probably you already know this, but essentially if you have an image, when it is on a computer, it is recorded a bunch of bytes. So for example, each pixel corresponds to the red, green, blue value of that pixel or other encodings for the color. So if you have a, say, 100 by 100 pixel image, you will get some matrix like this. This is 100 by 100. And each of these points or elements of that matrix would be the RGB value. Or if it's a grayscale image, it would be just grayscale value. So machine learning algorithms needs to, like, we want to develop machine learning algorithms that can handle many different types of data, images, text, audios. And you will see that what we talk about, all the methods that we talk about, or most of the methods we talk about, they basically ignore what type of data they are, whether images or text or something else. So we talk in a somehow abstract way about machine learning. We say that there is an input and there would be an output. But to make all these methods or be able to talk about all these different data types in a unified way, we can think of all of them as some form of input vector. So we can somehow convert the inputs, the image or audio or text, to some vector, input vector, which resides in some Euclidean space, like d-dimensional vector. So this is the strategy that takes you through this course. And this is sometimes called the representation of that input. So that matrix that we had, if we convert to a vector for an image, that would be a representation of that, that image in the computer to be used by machine learning method. And depending on how we can, and there, in some problems, there might be different ways to find this representation. And some representations are easier to manipulate and work with. So one reason that we use these vectors is that, well, vectors are great mathematical objects because we can think about, we can do things like linear algebra with them. We can add vectors to each other. We can multiply vectors by some matrices. We can do a lot of processing on vectors. So that's the one great thing about vectors. Okay, so there's a question here that said, does D, I think in R to the power of D means the number of features defined? Yeah, so this we can think of the dimension of the input, the number of features. So for example, if you have a 100 by 100 pixel image, grayscale image, we can define it as a 10,000 dimensional vector. So D would be 10,000. Okay, so here I guess I have the example. Yes, so it's a question.
Sophia.
Okay.
Yeah. Okay. So are there any methods that take input as a matrix instead of just vectors?
Input as a matrix is... Okay, so I guess you heard the question. I have to figure out if we have enough equal or not. But the question is that are there methods that can use vector matrices instead of vectors? So yes, but vectors and we can convert matrices to vectors easily. So that's why most methods directly consider them as vectors. There are some methods that benefit from the vectors matrix-like structure of the input. For example, so if this is a big matrix, these points are closer to each other. So some methods benefit from the regularity of structure that these points are closer to each other. If you convert this to a vector, the closeness of these points in this big matrix would be lost somehow. And some methods benefit from that. And there are other methods that we don't talk about, but say there are problems like matrix completion problems. So you have a matrix, but you don't know all the elements of it, and you want to fill the unknown values somehow, because under some conditions or assumption on the structure of the matrix. So those methods are derived assuming there is this matrix structure. Yeah, so let me just try to. Okay, so let's talk about this, the representation that we give to a computer, to a machine learning algorithm, which is in the form of like this data set of the which we call it, say, training data set. So what is training data set? Training data set consists of a collection of pairs of input, vector X, which belongs to D-dimensional space, and its corresponding target or output or label T. So depending on the problem that we want to solve, the targets might be different. So in the classification that we talked about so far mostly, T is an element of a discrete set, like 1 to C. So this is essentially corresponding to the apples and oranges. We say that apples are 1s, oranges are 2. So this would be our target. T would so belong to the set of 1 and 2. But then we have regression problem, which I think someone asked before, that T, the target or label, but this is not really a label, it's more like a target, is a real valued number. So it would be a number like 5.75 or something like that. And then also in some other problems, T, the target can have more structure. So for example, it can be an image itself, but we don't really talk about them in this course. So given these inputs, input vectors and corresponding T, so the training set, we would have a training set which would be this set of tuples of x1, t1, x2, t2 to xn, tn. So we have n different data points here, each of them in the form of input and output. And so I guess as a comment is that this superscript doesn't have anything to do with the exponentiation. It is just denoting which of the inputs we are. So I want to connect my iPad so I can write, but I can't. No, there is no blackboard. I mean, there's a blackboard, but behind this, so I can't use it. But there are other notations that people use. For example, you may use subscript instead of superscript. So, okay. So I think some of you are from, I guess many of you are from different areas of computer science, or sometimes not even computer science. I think we have people from psychology, and mechanical engineering and others. So what are the examples of regression and classification problems that you have seen in your, or you can think of in your domain? Let me see if there are. Okay, okay, so good. Regression, okay. House price prediction or time series. Okay, so that's a good example. Position varying with time. So I'm not, so is that regression or classification? Okay, classification is diagnosis. Okay, the answer to that is regression. Classification, diagnosis of disease or not. So one person has a disease or not, that's a classification. Classifying a tweet is trending or not. Okay, so that's good. So what about here? Yes.
So I'm in the area of control /rewards. So maybe one is if you're give you out some picture and you're trying to identify some like a wall or like a, I don't know, a box or something, you're trying to avoid it, the output would be like the position signs of it, and that would be a bigger regression.
Okay, so why is it, okay, so the question, the answer is if we see a wall or an object, and that would be an example of regression?
Yeah.
Okay, so what would be the target?
Well, trying to represent where it is. So.
Okay, trying to represent where it is, like maybe it is 3 meters away from your position. Yeah. Okay, so yes, I guess you can think of it as a regression problem. Right, yes, so if trying to find where the location of it, that's an example of regression problem. Okay, what else? Anyone here? Yes.
Weather prediction, temperature is an example of regression.
Temperature would be, so temperature would be an example of regression. So that's.
Weather, kind of weather that we have, whether it's rain or not, or when it's snow or not, then we have classification.
Okay, so the prediction, the problem of predicting whether it is going to be rainy or not, that's an example of classification. Okay, that's good. Okay, so there are other examples here. Classification in autonomous vehicles, stop sign, pedestrian, and etc. Okay, so I think classification is a special kind of regression. Usually that's not the way we define it, but I guess the way we define it here is that regression would be when the output would be real value, but classification would be the output would be discrete set. There might be a slightly different definitions elsewhere. In that case, essentially you say anything that has a T, doesn't matter what type of object it is, discrete or continuous, that would be regression. But that's not the definition that we use here in this course. So classification. Is this image of a lump a benign or malignant tumor? Okay, that's good. Regression. What price should I sell my house at? Kind of. Okay, so the price is real valued, but then it's I guess you can say that, like, if you know the data from the neighborhood, what is the prices of the houses sold in a neighborhood with similar structure to your house, like the number of bedrooms and things like that, then trying to predict the market based on your new features, that can be a regression problem. Okay, mechanical engineering application for regressions. Pressure output of a compressor based on input voltage and current. Okay. Classification, whether a system's operation is healthy or not. Okay, there are classifying text based on their content topics, yes. Classification, digit recognition, yes, and we'll see it later. Regression, at what speed should an autonomous vehicle drive? That's good, but okay, so I guess the problem of what speed it should drive, you can think of it as a planning problem, like in order to minimize the chance of accident or things like that. And probably, I mean, you can think of it more like a reinforcement learning problem, or if you have data sets of safe driving speed, you can think of it as a regression problem. Okay, so let's move on. So this is good. You have a lot of examples. Think about it, and actually I'm going to probably ask you to think more about it later as a part of exercises. So let's develop our first machine learning algorithm. Suppose that we are given a training set in the form of x1, t1, xn, tn for a classification problem, which means that t's are discrete values like 1, 2, 3, 4. And then suppose we are given a novel input data x, which does not belong to any of these x's necessarily, and we are asked to classify it. How can we do it? So I want your input here. Like I want you to think about simple approaches to do it. Yes.
Yeah, so one way could be to compute the distance between the new x and all of the x's, and then assign the label t to the closest or known x.
That's okay. Yes. So I guess you heard it. That's great. So basically, we look at the nearest neighbor, closest point, and then assign the same label as that. Is that clear? Okay, that's great. We have our first algorithm. So this is called nearest neighbors. Suppose we are given, I mentioned that the idea is, as you said, find the nearest input vector to x in the training set and copy its label. So that's the basic idea. And now, in order to kind of implement this idea or make it practical, we need to think about what nearest means. So when we talk about nearest, recall that each of our inputs are a vector, right? All x1 to xn are vectors, and the new point is also an x, so that's another vector. How can we measure distances, find the nearest point from this vector to another one? We need to compute the distances, right? So the great thing about vectors is that it's easy to compute distances. And the way we can do it, there are different ways, but one of them is through computing the Euclidean distance, which basically says that the Euclidean distance between xa and xb, 2 points, is the square root of each of the summation of each of dimensions xj, dimension j, from dimension j equal to 1 to d, between a and b, and then take the squared value of it, sum all of them, and then take square root of it. So that would be our distance. Yes. D, the question is that what is d, and the answer is d is the dimension of the x. So d is here. So x belongs to rd. So that's the dimension of it. So for image, if it's 100 by 100 image, d would be 10,000. So that's the distance between 2 images. So the algorithm would be essentially trying to find an example x star and t star from the stored training set closest to x. So if you compute the distance of each of xi's to x, like one is distance 0.2, the other is 0.5, the other is 10, compute all the distances and then take its label. So it goes away. Take that label of that nearest neighbor and assign it as a point, as our label. And so there's this note that we don't need to compute the square root actually for this algorithm, but I let you think about why that's the case. Okay, so let's try to see, understand what this algorithm is actually doing, or how it divides the space to different regions. So suppose these are points, I guess you see my mouse. So red points and blue points. We can compute something called Voronoi diagram, which is essentially divide this space to regions that are closest to each of these points. So these points, like this boundary that we have here, is the boundary that the distance between this red point and this boundary is the same as the distance of this other red point to this boundary. So this is kind of line there. And then we have this other point. So essentially, each of these kind of cells would be the points that are, or regions, subset of the state space, or not state space, input space, that is closest to each of these points. So here, for example, this white one is the corresponding closest to this blue one. So if we divide this space, input space in this region, those points that are gray are essentially points that become, if we query point here, for example, at the tip of my mouse, that would be labeled as a red one. And if it is the blue one, that would be pointed as blue one. So you see that the kind of input space is divided to different regions. Yes.
How do you define the boundary?
So essentially, those would be the points that are that region would be the points that are closest to that specific, say, red point. There is a kind of algorithm that we can compute it. It's called, this diagram is called Voronoi diagram. There's an algorithm to compute this Voronoi diagram, but that doesn't matter how it works or how we compute it. But the concept is that these points in these cells are the points that are closest to this red point. And for each of them, the same. I guess I didn't repeat the question, sorry. So the question was that how to define those boundaries.
I don't think also put it the other way around. Like if we pick a point, what is the closest blue or red point that we have?
Yes.
And then whatever we have that is gray, we already know the answer. That's what these diagrams are, right?
Yes. So the thing is that we can see it differently. Like we look at each point in the input space and see which one is the closest red or blue one, and then divide the space that way. So yes, essentially this is doing that way, but okay. And then, okay, so there is another concept that is important, is that called decision boundary, which is the boundary between regions of input space assigned to different categories. So if the order of points is like this, there would be this region, this boundary, which anything on one side of it is assigned blue, and anything on the other side would be assigned red. So depending on whether we are in left side or right side, the decision would be different. And we can do the same thing for 3D. I mean, this image, I don't know if you get much intuition from it or not. This is just 3-dimensional one. Basically, we can define a decision surface in 3D, but that's difficult to visualize. Okay, so that's the idea of nearest neighbor. The problem with nearest neighbor is that it can be sensitive to noise or mislabeled data. So if you have a point that should be actually apple, but somehow you mislabeled it as orange, that causes an error. So what can we do is that instead of just looking at the closest point, we look at the k closest point or k nearest point. And k can be a number larger than 1. So for example, we can look at 3 nearest points or 5 nearest points or 10 nearest points. And this essentially, the algorithm would be the same or it's very similar to the previous one, but you need to essentially look at for each data point that you query, your X, you find the closest K points, 5 points, for example, and then see what are the labels. And you see that maybe 4 of them are apples, 1 of them is orange. Your solution would be apple. Your output of the algorithm would be apple. So you take a majority votes between them. And this is this algorithm is essentially trying to do that. Okay, and how it looks like. So this is another example. So these are kind of, I guess, yellow, orange, and blues. The decision surface, decision boundary is shown here. So you see it's very rugged boundary. So here, if we have a bunch of maybe, say, there's one data point that is blue in the middle of a lot of other oranges. Is it a noise or is it actual structure? So if you use K equal to 1, this neighborhood would be called blue one. But then as we increase it, like we increase K equal to 15, you see that the decision boundary becomes much nicer and smoother. And even though there are some bunch of red, blue points here, for any point here, the majority of like the closest 15 one, the majority would still be orange. Okay, so let's see. So we have a, no, here, okay, so there is a comment here that boundary is only a line in 2 dimension. But you see that, no, actually, this is a boundary here. This is 2-dimensional data, but the boundary is not 2-dimensional. I think I know what you're talking about. There are methods that use linearly separates the classes, and those methods that would be a line, but not, for example, a method like K nearest neighborhood. Okay, so there's another question that is saying that how does it impact accuracy when we increase the K from 1 to a larger number greater than 1? So that's actually a good point. So there is an answer, but I'm going to give an answer about that. So I think, unfortunately, I'm not going to finish this lecture. But I leave these for now. Maybe I talk about logistics a little bit, because many of you want to decide on taking the class based on that. Maybe we can finish it in 3 minutes, hopefully. If not, the slides are there. So this is a broad introduction to machine learning. We talk about supervised learning, unsupervised learning, and reinforcement learning, mostly about supervised learning, maybe 60–70%, but we have lectures on others. The coursework is aimed at the advanced undergrad or the first-year grad, or from other fields that are not computer science. We need to know linear algebra, calculus, probability, and statistics, and also be good in programming. So these are the things that you need to know, the kind of, I mentioned the level of things that you mentioned. So there's a course web page. I sent an email. I think you received it. We use Quarkus for announcement. I keep sending an email because people on waitlist are not on Quarkus. But after a while, probably I will stop doing that. We use Piazza for discussion. So that's a way of doing it. Okay, so the important thing is that this course is offered as in person. So you're not supposed to, or after, I guess, the 23rd or something, we don't need to have a virtual version of the course. But because of COVID, I'm thinking that maybe it's a good idea to try to reduce the density of the class and encourage all of you to not come to the class. Whether the course becomes virtual completely or not, I guess it depends on the university's policy. I don't think we can decide not to come anymore, because there should be an in-person component of it. And I enjoy in-person very much. It's much more fun. But there's a risk. So synchronous via Zoom, the lectures will be recorded. and I put it probably on YouTube. But know that it takes a while. Like each lecture, just converting a video takes 2 hours. And practically, from my previous experience, I post it on Friday or Saturday, not Tuesday evening. So in person, try to avoid, don't come sit close to each other. I guess that's good. Wear a mask all the time, get vaccinated if you haven't already, and if you can. And then the other thing, okay, I noticed is that you shouldn't take pictures. Use cell phone or something like that, unless you get permission beforehand. But given that everything is already on slides, probably don't need it. You may download it. I mean, it will be on YouTube probably, but shouldn't distribute it. So if you are on Zoom, unmute yourself unless you have a question. And I guess that would be a good way. I try to monitor the chat, but it's kind of cognitively challenging. Like I have to context switch, so I may not be able to follow what's happening on the chat. But I try. I like trying a few times. I encourage you to turn your videos on. So most of all of you, I guess, were off, but I like also to see you. So, but you need to know that if you do it, if your video might be recorded. I think it happens if you talk. So the focus would be on you and that would be recorded. And there is, if you become sick, there is a procedure at university how to deal with it. I mean, if it is minor thing, you need few more days, 2-3 days, you can contact me. But if it's major, like week or 2, you need to ask for extension. You need to go through the official procedure. But I try to be as accommodating as possible. So if you get sick, you need 2 more days for assignment, that's okay, but just let me know beforehand, not on the deadline. Unless, I mean, it's emergency, then we don't have any choice. Course evaluation, hopefully nobody comes. Course evaluation is that this is tentative, it might change, but that's what I'm thinking right now. We have 4 assignments, each of them 10%. So it will be a combination of mathematical derivations, some simple proofs, and programming exercises. I think based on my experience, most of the time will be taken programming assignments. There is research project that will be 30% of the course. You need to have a research proposal, written reports, peer reviewing. I'm not sure if you do it or not, and probably class presentation, but that depends on how many students actually enroll by the end of the course. Like if we can fit, if there are 20 groups, we can present it in 1 lecture, each 5 minutes or so. But if there are 30, 40 students, probably can. There is no exam or final or midterm exam, but there's a take-home test. So you will have a few days, 2 days maybe, to write basically what you know about the course. The other thing that I'm thinking is questions. So after each lecture, you need to think about some questions and submit that question through some website. So you need to read some papers, and so that will 10% probably, that is a bonus point. So I guess I will make, are your students coming? Okay, so collaboration. So so this course load is high. It's not, this course has never been easy. So not because it's difficult, but because it takes a lot of time. So I added a project because it's the introductory in grad level course, not undergrad. We don't have projects in undergrad usually. But to make it simpler, I'm thinking of you can collaborate on assignments, but with some conditions. So you can discuss the assignments with maybe 2 others, so you can have a group of 3. You can write the code together, but you need to write your report separate. So 3 separate reports, so they shouldn't be exactly the same, but you can share the same source code, or you can, but also you need to mention who you have been working. These are tentative, like 90% this is going to happen unless it changes something, but that's my idea. For projects, you need to have a team of probably 3 students, but that exact number depends on how many students are enrolled. If, say, all of you decide to drop the course and we will only have 30 students, then you can have teams of 2 maybe, or 1, like if you want. The idea is that we keep 15, 20 teams at most, so we can present them. Collaboration take-home tests and questions are not allowed, so for only homework and project. Late submission, there's a policy, so every day 10% up to 3 days. You can ask for extension. There are several more advanced machine learning courses here. Many of them are based on this one. So we have a course on neural networks, the probabilistic learning. So these are, I guess we have it in winter semester. There's a course on reinforcement learning, but not this year. The other thing I kind of want to mention is that this course has a long history. It's 2515. It previously used to be 400 level course, 411, and the grad level code name probably the same number. It got converted to 300 level course. And what I'm teaching you actually would be based on what I taught at 300 level, kind of upgrade, adding a bit more material to make it more like a grad level course. And have a project, so it would be more like research-based one. But the level, like third-year students, fourth-year students should understand should understand all of it essentially. And a lot of credit goes to all the professors. So most of these slides have been around and modified. Okay, stop showing something here for me. So these slides have been developed by many people. I modified some of them a little bit, but there's a lot of credit goes to Roger Grosse, Murat Erdogdu, Richard Zemel, Juan Carrasquilla, and many others that I may not know what was the actual evolution of these things. But so this is a kind of joint effort. And I guess the warning is that this is not a difficult course content-wise, but it takes a lot of time. I try to make it a bit lighter by allowing to have collaboration on homework. But you should know that from my experience, people can't do it, just start work on homework the one day before. It takes a lot of time. There's some useful resources that are on our website, so I don't go through. Okay, so this is good, except that we haven't finished a bunch of our methods, but I try to continue. These 5-10 slides left next time, and then we go to the next lecture. That's all. Thank you. Okay, so right. So let me see if answer. Okay, so the question is, yeah, if there are any question, yes, just please ask me. I'll try to repeat for not forget repeating this.
So, can you hear me?
I'll try to answer some questions here. Will assignment be available to people register in the course to practice? Yes, so assignments will be available online. Will the course be online for the rest of semester, or will be decided on that later? My intention is to do it for the whole semester. I know better how difficult it is in a week or two, but that's my intention. Is the research project? I answered that. I like access to assignment tests too, please. So you have access to assignments. If you haven't registered, it's online, but I won't share the take-home test. Can you explain the question part a bit more? I do it later. Okay, so I guess I have to finish this. Have a good day.